Imagine staring up at the night sky, those distant burning stars. They're just these colossal furnaces out there,
Unbelievable scale.
representing immense, almost unimaginable power. And it's all fueled by a process that literally built the elements around us.
Exactly. Stellar nucleosynthesis.
For centuries, humanity has dreamt of bringing just a fraction of that power down here to Earth, putting quite literally a star in a bottle.
A very evocative phrase.
And today, that dream isn't just science fiction anymore. It feels like it's closer to reality than ever before.
It really does. The progress has been accelerating.
Welcome to the Deep Dive. This is where we take your curiosity, dig into the sources, and really unpack the most important nuggets of knowledge and insight. Today, we're embarking on this incredible journey into the ambitious and endlessly fascinating world of nuclear fusion.
It certainly is fascinating.
We'll try to strip away some of the hype and explore the foundational physics, the absolutely colossal engineering challenges, and also this surprising new commercial race that's heating up to bring this clean, potentially limitless energy source to life.
It's quite a journey spanning from, the cosmic scale of distant suns right down to the microscopic interactions happening inside a plasma. We'll reveal not just what groundbreaking work is happening in these cutting-edge labs, but really why it matters so profoundly for our energy future.
Right.
We'll delve into the ingenuity, the breakthroughs that have really shifted paradigms, and also the significant hurdles that, frankly, still remain. We want to offer you a shortcut, really, to truly understanding this pivotal technology. So yeah, let's begin to truly unpack this incredible quest.
Okay, so to really grasp this colossal undertaking, we first need to strip away maybe the science fiction layer and understand the fundamental process, fusion itself.
At its very core, yeah.
At its heart, it's a reaction where two or more light atomic nuclei, think hydrogen isotopes, they combine under extreme pressure and heat
Immense pressure and heat?
to form a single heavier nucleus, like helium. And that tiny, almost imperceptible difference in mass between what you started with and what you end up with.
That tiny bit of missing mass.
That mass isn't lost. It's converted into pure energy, precisely following Einstein's iconic EMC-Wes.
And while the concept of EMC-Wes is, pretty familiar, what's truly astonishing here is the scale of this conversion. Think about it. Even a minuscule, almost unmeasurable amount of missing mass, when you multiply it by the speed of light squared, which is just a truly enormous number,
Huge number.
it unleashes an absolutely colossal amount of energy. This makes fusion incredibly efficient compared to, say, any chemical reaction, like burning fossil fuels. And it's even more potent, significantly more, than nuclear fission, which is what current nuclear plants use.
So it's not just a lab curiosity.
Oh, not at all. This process is the fundamental engine of the entire observable universe. It's constantly powering our own sun and every other star you see twinkling out there. It really is the universe's ultimate power source.
Okay, so if it's the engine of the universe, how does the sun manage this incredible feat? I mean, it doesn't have giant lasers or magnets, right? And what does that mean for us trying to replicate it here?
Right, that's the key difference. What's fascinating is how the sun does it almost effortlessly. Its immense gravitational force naturally compresses and confines hydrogen plasma. The sheer weight of the star does the squeezing. And it does this at temperatures around 15 million degrees Celsius.
Only 15 million. Sounds almost cool compared to what we're aiming for.
Huh. Relatively speaking, yes. Those conditions are sufficient for fusion in the sun because of the sheer volume and density, and crucially, the consistent long-term confinement provided by gravity. But here on Earth, obviously, we don't have that cosmic gravity. We can't just build a star.
Unfortunately not.
So to compensate for lacking that natural confining force, we have to create even more extreme conditions ourselves, conditions far beyond what the sun actually needs in its core.
Like how extreme?
We're talking about temperatures exceeding 100 million degrees Celsius. And then the really tricky part. We have to hold that super hot plasma within a very small confined space for long enough for fusion to happen without it touching anything.
Which would melt instantly.
Instantly. It's truly an engineering marvel just to get to that point. It's a testament to human ingenuity trying to mimic these stellar processes, but without the star's natural advantages.
And the potential reward for this monumental effort, I mean, the numbers I've seen are quite remarkable. They suggest a future that could completely redefine energy.
They really are staggering. Fusion has the potential, theoretically, to generate 4 million times more energy per kilogram of fuel than burning traditional fossil fuels like oil or coal.
4 million times.
And even compared to existing nuclear power plants, which use fission-splitting heavy atoms, fusion promises about 4 times more energy per unit mass of fuel.
That's just hard to get your head around.
It really is. This isn't just a small improvement. It hints at an energy future where fuel scarcity could genuinely become a relic of the past. We're talking about an almost inexhaustible power source, if we can crack it.
Okay, so out of all the possible fusion reactions you could try, the one that gets the most attention, the most research, and seems the most promising for actual power generation here on Earth is called Deuterium-Tritium fusion, or DT. Why that specific pairing? Why D and T?
Yeah, the DT reaction is really favored because, relatively speaking, it requires the lowest minimum temperature to get going. We're talking only about 100 million Kelvin.
Only 100 million. Still sounds pretty hot.
Oh, it is. I use low in heavy air quotes because that's still an astronomically hot temperature by any earthly standard. But in this specific reaction, a deuterium nucleus that's a stable isotope of hydrogen with 1 proton and 1 neutron, it fuses with a tritium nucleus.
Which is the unstable one.
Right, another hydrogen isotope, but with 1 proton and 2 neutrons. It's radioactive. When they combine under those extreme conditions, they form a stable helium-4 nucleus, 2 protons, 2 neutrons, plus a free, very high-energy neutron.
The neutron again.
Exactly, and a substantial amount of energy, about 17.6 mega electron volts, or MeV. That MeV unit really quantifies the immense power released just from rearranging those few particles. Scientists identified this DT reaction as kind of the energetic sweet spot, the most achievable reaction for a first-generation power plant. Other reactions need even higher temperatures.
Okay, so DT it is. Now, the fuel itself for this reaction, you mentioned deuterium and tritium. It sounds like this presents what you might call a double-edged sword, right? Abundance on one side, but scarcity on the other.
Precisely. That's a perfect way to put it. The fuel availability for DT fusion presents both a significant strength and, frankly, a key challenge, maybe the key challenge besides confinement and materials.
Okay.
Deuterium, for instance, is the good news story. It's a stable hydrogen isotope. It's incredibly abundant and relatively inexpensive to extract directly from seawater.
Just from regular water.
Pretty much, yeah. It occurs at a ratio of about 1 deuterium atom for every 6,500 regular hydrogen atoms in water. It sounds rare, but there's so much water. Just 1 gallon of seawater contains enough deuterium to produce, through fusion, as much energy as burning 300 gallons of gasoline.
Wow.
So that provides a practically limitless supply for millions, maybe billions of years. A huge advantage.
But tritium.
Tritium, that's the other edge of the sword. Tritium is the rare isotope. As I said, it's radioactive with a relatively short half-life of just over 12 years.
So it decays away fairly quickly.
It does, and it's incredibly scarce in nature. We simply can't dig it out of the ground or filter it from the sea in meaningful quantities. There are only a few tens of kilograms available globally, mostly produced as a byproduct in certain types of nuclear fission reactors, specifically heavy water reactors.
So we don't have a big stockpile waiting.
Not at all. This scarcity is a fundamental barrier to any long-term commercial fusion power using the DT cycle unless we can address it directly within the reactor design.
Okay, so to overcome this tritium scarcity, future fusion reactors need to be self-sufficient. You're saying that they'll actually have to breed their own tritium right there inside the reactor itself. That sounds incredibly clever, almost like alchemy.
It's not just clever, it's absolutely critical. It's a non-negotiable requirement for any future commercial viability of DT fusion power. Without on-site breeding, the fuel supply simply wouldn't be sustainable beyond maybe a few initial experiments.
So how does that work, this breeding?
It happens in a special component called a tritium breeding blanket. This blanket ingeniously lines the inner walls of the reactor vessel surrounding the plasma.
Right.
Inside this blanket are lithium-containing materials. These could be solid ceramics like lithium orthosilicate or maybe molten salts containing lithium. Now remember those high-energy neutrons produced by the DT reaction?
What's carrying most of the energy?
Exactly. They fly out from the plasma and smash into the lithium atoms in the blanket, particularly the lithium-6 isotope. When a neutron hits lithium-6, the reaction produces a helium atom and, crucially, a new tritium atom.
So the neutron gets consumed, but you get a tritium atom out.
Precisely. This continuous process, fusion makes neutrons, neutrons hit lithium, lithium makes tritium, tritium fuels fusion. This closes the fuel loop. It makes the reactor self-sufficient in its most challenging fuel component. ITER, for instance, the big international project, plans to test several different breeding blanket concepts to figure out which ones are the most effective and efficient for future commercial reactors. They recognize this is a vital, integrated part of the whole puzzle.
Okay, but this raises that important question again. If this high-energy neutron is absolutely essential for breeding the tritium we need, is it also the source of some of the most profound, maybe even show-stopping engineering problems elsewhere in the reactor?
Absolutely. It's the ultimate paradox, the real double-edged sword of DT fusion. While that high-energy neutron is crucial for tritium breeding and, importantly, carries away 80% of the fusion energy, which is the heat we want to capture to make electricity,
Right.
it also relentlessly bombards the reactor's structural materials, the walls, the blanket structure, everything.
And these aren't gentle taps, I imagine.
Not at all. These neutrons, traveling at incredible speeds with 14 MeV of energy, literally knock atoms out of place within the metal crystal lattices of the reactor components. This causes significant material degradation over time. We call it radiation damage.
So to put this in perspective, the problem of the fuel cycle successfully breeding enough tritium is intrinsically linked, hardwired you could say, to the most difficult materials science problem, designing materials that can withstand this constant, incredibly harsh neutron radiation for years, decades even, without falling apart or becoming too radioactive.
Exactly. It's a truly complex interplay of challenges, a fundamental limit we absolutely have to overcome for fusion power to be practical.
Okay, let's step back for a second to the microscopic level again. We keep talking about these extreme temperatures, hundreds of millions of degrees. Why exactly do we need it to be that hot? Why can't we just, gently persuade the nuclei to fuse at lower temperatures?
If only. Well, you have to remember, atomic nuclei are all positively charged, right? Both deuterium and tritium nuclei carry a positive charge.
Okay, like charges repel.
Exactly. Basic physics like charges repel each other. This is described by Coulomb's law, and this electrostatic repulsion creates a pretty formidable energy barrier between two approaching nuclei. Think of it like trying to push the north poles of two strong magnets together.
Gets harder the closer they get.
Precisely. To get these positively charged nuclei close enough for the powerful but very short-range nuclear strong force to take over and actually bind them together, which is what fusion is, they need immense kinetic energy. They need to be moving incredibly fast to overcome that repulsion.
And temperature is just a measure of kinetic energy, right?
Essentially, yes. Temperature is a measure of the average kinetic energy of the particles. So needing hundreds of millions of degrees Celsius is just another way of saying the nuclei need incredible kinetic energy, incredible speed to have a chance of overcoming that Coulomb barrier and fusing. At these astronomical temperatures, the fuel isn't a gas anymore. It enters the fourth state of matter, plasma. A hot, electrically charged soup of positive ions, the nuclei, and free electrons, all zipping around chaotically.
But I've heard, and this sounds a bit weird, that classical physics, just smashing them together hard enough, doesn't tell the whole story here. So it's not just about brute force.
Not entirely, no. And this is where it gets really fascinating and, frankly, a bit counterintuitive. This next point is crucial. It turns out there's a quantum mechanical effect at play.
Ah, quantum mechanics. Things are about to get strange.
They always do. Quantum mechanical tunneling, a phenomenon first understood by the physicist George Gamow in the context of radioactivity, allows a certain fraction of nuclei to essentially tunnel through the Coulomb barrier, even if they don't classically have enough energy to jump over it.
Tunnel through it, like a ghost through a wall.
That's a common analogy, yeah. It's like they're exploiting the fuzzy probabilistic rules of quantum mechanics that govern the tiniest scales. They sort of borrow the energy for a fleeting moment to appear on the other side of the barrier, defying our everyday classical intuition. It's not brute force, it's quantum finesse, you could say. Nature giving us a bit of a helping hand.
So this isn't just some quirky theoretical detail. It's actually important for making fusion happen, like a fundamental cheat code provided by nature.
Precisely. That's a great way to put it. This quantum tunneling phenomenon isn't just a footnote. It's a fundamental aspect that makes fusion possible at the temperatures we can potentially achieve. It effectively lowers the energy bar, the temperature requirement for fusion. This defines what scientists call the Gamow window. It's not a physical window, but rather represents the optimal conditions, a specific range of energies and temperatures where fusion reactions are most likely to occur efficiently. It's the sweet spot that benefits from both having enough classical kinetic energy and getting a boost from quantum tunneling.
Wow.
Without this quantum finesse working alongside the brute force high temperatures, the temperatures required for fusion would be astronomically higher, perhaps truly unachievable on Earth. So fusion is far more feasible than it would be otherwise, thanks to this weird quantum effect. It's a testament to the elegant complexities of the universe, really.
Okay, so we need high temperatures, aided by quantum tunneling. But for a fusion reaction to be truly useful, to be more than just a flash in the pan, it has to be self-sustaining, right?
Yeah.
It needs to produce more energy than we pour in to get it started and keep it going.
Exactly. That's the ultimate goal for a power plant, net energy gain.
And this critical principle, this target, is elegantly quantified by something called the Lawson Criterion. I've also heard it called the triple product because it combines three incredibly critical variables. What are they?
You can think of the Lawson Criterion, or the triple product, NT, as the ultimate recipe for achieving a self-sustaining fusion reaction, or ignition. It combines three key ingredients. First, temperature T. As we've just discussed, the plasma must be hot enough, hundreds of millions of degrees, for those nuclei to overcome the Coulomb barrier and tunnel efficiently. That's ingredient number one.
Got it. Hot enough.
Second, density, N. There must be a dense enough concentration of nuclei in that plasma. You need enough fuel particles packed together to increase the probability of them actually colliding and reacting. If they're too sparse, even if they're incredibly hot, they just won't meet often enough to sustain a significant reaction rate.
Okay, dense enough. Like rush hour traffic versus an empty highway.
Good analogy. And third, confinement time. D pronounced tau sub E. The plasma, this hot, dense soup, must be held together, confined, for long enough for a sufficient number of fusion reactions to occur before the plasma cools down or expands and dissipates. You need to keep the party going long enough.
Temperature, density, confinement time. All three need to be high enough.
All three are equally crucial, and they trade off against each other to some extent. You need the product of all three, density times confinement time times temperature, though often it's just density times confinement time at a given sufficient temperature, to reach a certain threshold value. If any one of those factors is too low, the reaction won't sustain itself, no matter how good the others are. You'll put more energy in than you get out.
So all three of these parameters, temperature, density, and confinement time, need to be cranked up high enough simultaneously to achieve a very specific and highly sought-after state. A burning plasma. What's that exactly?
A burning plasma is kind of the intermediate holy grail on the way to full ignition. It's a state where the energy released from the fusion reactions themselves, particularly from the energetic alpha particles, the helium nuclei, produced in DT fusion, which stay within the plasma, is enough to significantly heat the surrounding fuel.
So it starts heating itself.
Exactly. It starts to become self-heating, reducing or even eliminating the needed for continuous external heating power to keep the plasma hot. It becomes more like a self-sustaining chemical fire, or indeed like the core of a star.
Right.
The primary goal of most modern large fusion experiments, like ITER, is therefore to achieve a triple product value that results in a net positive energy gain. This is often represented by the symbol Q.
Q factor.
Right. Q is simply the ratio of the fusion power produced out of the plasma to the external heating power you put into the plasma to keep it hot. Achieving Q greater than 1, Q1, means you got more fusion power out than heating power you put in. Q1 is scientific breakthrough. Quinfinity would be full ignition, where no external heating is needed at all. And Q10, ITER's goal, would be a strongly burning plasma, producing 10 times more power than needed to heat it.
So achieving Q1 is the big scientific milestone, proving we can actually light our own miniature sun and get more energy out than we put in to heat it.
Precisely. That's the scientific proof of principle that fusion energy is possible.
Okay, so we've outlined the incredible power, the extreme conditions needed, temperature, density, confinement time, the triple product, and the fuel cycle challenges. Now, the grand challenge shifts to how we actually create and contain those conditions here on Earth, reliably and controllably, without the sun's handy gravitational cheat code.
Right. How do you build the bottle for the star?
Exactly. This leads us to two main, ingenious yet fundamentally different paths that scientists are pursuing to bottle the star. Let's start with the one that's maybe more established, magnetic confinement fusion, or MCF. So magnetic confinement fusion. The name kind of gives it away. It leverages the fundamental fact that plasma, being made of charged particles, positive ions and negative electrons, is strongly influenced by magnetic fields.
That's the key insight. Charged particles can't easily cross magnetic field lines. Instead, they're forced to spiral along them, like beads on a wire.
Which is ingenious, right? It allows this incredibly hot plasma, hotter than the sun's core, to be held within a vacuum chamber without ever touching the physical walls.
Which, as we said, would melt or vaporize instantly. The magnetic field acts as an invisible, immaterial container. Hashtag tagged, hashtag the Tokamak, the global standard.
Now, within MCF, the most studied and currently most advanced concept, the one that projects like ITER are based on, is the Tokamak. Well, that's a Russian acronym, isn't it?
It is, yeah. It stands for toroidal chamber with magnetic coils. Catchy. So, picture a donut shape, a torus. That's a vacuum chamber. Inside, a tokamak creates a complex helical magnetic field, basically a twisted magnetic cage to trap the plasma. How does it make that twisted field?
It uses two main sets of magnetic fields working together. First, there's a very strong toroidal field running the long way around the donut. This is generated by large external coils wrapped around the donut chamber.
Okay, that confines particles going around the loop. Mostly, yeah. But you also need a second field, the poloidal field, which runs the short way around, sort of looping through the donut hole. In a tokamak, this crucial poloidal field is generated by inducing a powerful electric current to flow within the plasma itself.
So the plasma carries its own current, like a wire.
Exactly. Millions of amps, typically. This plasma current creates the poloidal magnetic field, and when you combine the toroidal field from the external coils with the poloidal field from the plasma current, the resulting magnetic field lines twist into a helix. This helical shape is much better at confining the spiraling particles and keeping them away from the walls for longer times.
Clever. But you mentioned inducing the current in the plasma. Does that cause any issues?
It does. While incredibly effective for confinement, a major drawback of the standard tokamak design is its inherently pulsed nature. The method used to induce that large plasma current relies on a constantly changing magnetic flux through the central hole of the donut. It works just like a giant transformer, with the plasma acting as the secondary winding.
Like charging it up?
Sort of. To sustain that current using induction, you need to continuously ramp up the magnetic field from a central solenoid, but eventually you run out of magnetic flux swing. You have to reset it. This forces the reactor into a pulsed stop-start operation. You heat the plasma, run the current, fuse for a while, then shut down, reset, and start again.
That doesn't sound ideal for a power plant feeding the grid.
Not at all. It's a huge hurdle for continuous electricity generation, which is what a power plant fundamentally needs to do. This raises a really important question for power plant design. How do you build a commercial reactor based on a standard tokamak that operates only in pulses? Managing the thermal cycling, the grid stability, it's very challenging. There are ideas for advanced tokamaks using non-inductive current drive methods, but they add complexity.
And the biggest name in tokamaks, and what everyone talks about, is ITER, this massive international project. What's its specific mission?
ITER, the International Thermonuclear Experimental Reactor being built in France, is a truly global undertaking involving 35 countries collaborating. It's designed to be the world's largest and most powerful tokamak by far. Its main goal is monumental, to demonstrate a positive energy gain of Q10. Remember Q?
Right. Fusion power out divided by heating power in. Q10 means 10 times more power out.
Exactly. ITER aims to produce 500 megawatts of thermal power from the fusion reactions, while only needing 50 megawatts of external heating power to keep the plasma hot. Achieving that would be a huge leap forward, demonstrating a strongly burning plasma and validating many key technologies needed for a power plant.
But it hasn't been smooth sailing, has it? We hear about delays and cost increases.
No, it hasn't. And that's perhaps not entirely surprising for a first-of-a-kind project of this immense scale and complexity, especially one involving intricate international coordination and pushing the boundaries of so many technologies simultaneously. The initial budget was around $5 billion, but estimates now range from $18 to $22 billion, with some independent analyses placing the total lifetime cost, including operation, much higher, maybe $45 billion to $65 billion.
Wow, that's a big jump.
It is, and the timeline has slipped too. First plasma, which is the very first time they actually create plasma in the machine, was originally planned much earlier, but it's now slated for around 2033, 2034. Full power operation with deuterium and tritium aiming for that Q10 goal isn't expected until maybe 2039 or even later.
Why the delays and cost overruns? Is it just bad management?
It's more complex than that. Often it's due to unforeseen challenges in manufacturing very high-tech components to unprecedented tolerances, resolving difficult material science issues discovered along the way, the sheer R&D nature of building something that's never been built before versus just production, and undoubtedly the logistical complexities of coordinating components and schedules across dozens of countries and industries. It truly highlights the immense scale and profound difficulty of global engineering at the absolute cutting edge. Hashtag, the Stellarator, the steady alternative.
Okay, so Tokamaks are the front runners, but they have this pulsed operation issue, and ITER shows the scale challenges. Given those hurdles, what if you could achieve continuous steady-state operation inherently, bypassing that pulsed nature altogether? That's where the Stellarator comes in, right? An alternative magnetic confinement approach.
Indeed, the Stellarator is another toroidal, donut-shaped magnetic confinement concept, actually invented before the Tokamak, but it takes a very different approach to creating that necessary twisted magnetic field.
How so? No plasma current.
Exactly. Unlike the Tokamak, the Stellarator uses only complex, highly non-planar external magnetic coils to generate the entire confining magnetic field, including the twist. It doesn't rely on inducing a large current within the plasma itself.
So the coils themselves create the whole magnetic cage.
Precisely. These coils are often incredibly intricate, twisting and bending in 3 dimensions in very precise ways. Designing them requires massive supercomputer simulations, but the result is a magnetic field structure that inherently provides confinement without needing that potentially unstable, disruption-prone plasma current.
And the big advantage is?
The big advantage is twofold. First, it generally offers superior plasma stability compared to Tokamaks, being less prone to sudden disruptions where confinement is lost. And second, critically, it enables continuous, steady-state operation. Since there's no need to inductively drive a plasma current, a Stellarator can, in principle, run continuously for as long as you can fuel it and remove the helium ash. That's a non-negotiable condition for any truly practical commercial power plant.
Is anyone building large Stellarators to test this?
Yes. The world's largest and most advanced Stellarator currently operating is Wendelstein 7X, or W7X, at the Max Planck Institute for Plasma Physics in Germany. It was built specifically to demonstrate the feasibility of high-performance, steady-state operation in a Stellarator. Its design features incredibly complex, optimized superconducting coils.
And W7X recently had a major breakthrough, didn't it? Something about the triple product.
It did indeed. Recently, W7X achieved a significant milestone, setting a new world record for the fusion triple product specifically for long plasma pulses in a Stellarator configuration. They achieved high temperatures and densities for durations significantly longer than typically achieved in Tokamaks at similar performance levels without resorting to pulsed operation.
So what does this achievement really mean for the future of fusion? Does it put Stellarators ahead of Tokamaks?
It's incredibly significant. It means Stellarators can indeed achieve high-performance plasma confinement in a steady state. This validates the Stellarator concept as a viable, perhaps even preferable, alternative path to fusion power, one that offers inherent advantages for continuous electricity generation needed for the grid. It doesn't necessarily put them ahead. Tokamaks still hold the absolute record for the highest instantaneous triple product achieved in pulsed operation. But it proves that the steady-state advantage of Stellarators is real and achievable at high performance. It strengthens the case for diversity in fusion approaches, showing there isn't just one right way to bottle a star, and that continuous operation is indeed achievable in a magnetic confinement device. It gives us another strong horse in the race.
Okay, so magnetic fields, whether in Tokamaks or Stellarators, offer one elegant, continuous, or potentially continuous way to contain the plasma. But humanity is also exploring a fundamentally different, almost explosive approach that bypasses magnets entirely. Let's talk about inertial confinement fusion, or ICF.
Right, moving to a completely different strategy. Inertial confinement fusion, ICF, aims to initiate fusion not by holding plasma steady for long periods, but by causing a tiny amount of fuel to fuse incredibly quickly before it has time to fly apart.
How do they do that? Lasers?
Primarily lasers, yes, extremely powerful ones. ICF works by rapidly compressing and heating a tiny fuel pellet, usually containing deuterium and tritium, using intense beams of high-energy lasers, or sometimes particle beams or pulsed magnetic fields in variations of the concept. It's a blink-and-you-miss-it kind of reaction happening in mere nanoseconds.
So what's the principle? Just blast it.
It's more sophisticated than just blasting it. The principle is implosion. Imagine that tiny fuel pellet, maybe the size of a peppercorn, often encased in a shell. Hundreds of high-energy laser beams are focused precisely onto the outer surface of this target, or sometimes onto the inner surface of a small metal can called a hohlraum, which then converts the laser light into X-rays that uniformly irradiate the pellet. This intense energy rapidly heats the outer surface of the target capsule. This causes the outer layer to vaporize and ablate, essentially, blow off almost explosively.
Like a rocket engine.
Exactly like a microscopic rocket engine. By Newton's third law, this rapid outward ablation creates an equal and opposite reactive force, driving a powerful shockwave inward toward the center of the fuel pellet.
Crushing the fuel.
Precisely. This inward rushing spherical shockwave acts like a gigantic symmetrical vise, compressing the DT fuel inside to densities hundreds of times that of lead, and simultaneously heating the very central part of the fuel to those extreme temperatures needed for fusion over 100 million degrees Celsius. It's like creating a microscopic supernova for a fraction of a second.
So you're creating a tiny, super dense hotspot right in the middle, and that ignites the rest.
Exactly. The clever part is you don't need to heat the entire fuel pellet to fusion temperatures initially. The central idea is to efficiently compress the fuel and create a small central hot spot that reaches ignition conditions first. Once that hot spot ignites, the fusion reactions start, producing those energetic alpha particles, helium nuclei. These alpha particles fly out and deposit their energy into the surrounding denser but still relatively cold fuel. This rapidly heats the adjacent fuel layer to fusion temperatures, causing it to ignite as well.
So the burn spreads outwards.
Yes, the reaction spreads outward from the central hotspot through the compressed fuel in a wave, a process known as propagating burn. The whole thing happens incredibly fast. The inertial part of the name refers to the fact that the fuel is held together only by its own inertia, basically. Its resistance to acceleration for the brief nanoseconds of the fusion burn, long enough for the reaction to propagate before the whole thing blows itself apart. You don't need magnetic fields because it's over so quickly.
Right, the inertia confines it just long enough. Okay. Now, the biggest player in laser-based ICF is the National Ignition Facility, or NIF, at Lawrence Livermore National Laboratory in the U.S. It's got the world's most powerful lasers, right? And it has missions ranging from nuclear weapons science stockpile stewardship to, crucially for our discussion, achieving energy ignition for potential power applications.
That's correct. NIF is an incredible facility with 192 giant laser beams converging on that tiny target.
And on December 5th, 2022, NIF made genuine history. They achieved something remarkable.
They absolutely did. NIF achieved what's called scientific ignition, or sometimes target energy break-even, for the very first time ever in a controlled laboratory setting. It was a landmark moment for fusion research globally.
What exactly happened in that experiment?
In that groundbreaking experiment, the fusion reactions within the DT fuel pellet produced 3.15 megajoules, MJ, of energy. The crucial part is that this was more energy than the amount of laser energy that was delivered directly to the target to start the implosion, which was 2.05 MJ.
So more energy out than in.
More fusion energy out of the target than laser energy delivered to the target, yes. This yielded an energy gain factor, that Q value again, but defined slightly differently for ICF, Q target equal fusion energy out laser energy delivered, of Q1.54.
Ooh, greater than 1.
Q greater than 1. This is a monumental breakthrough in physics. It unequivocally proved that achieving a net energy gain from fusion reactions in a controlled setting, a self-sustaining fusion burn, is fundamentally possible here on Earth. It demonstrated the feasibility of the whole implosion and propagating burn concept, a huge scientific success.
Okay, here's where it gets really interesting, and where, reading the headlines versus understanding the details is crucial. We need to be really clear for you, our listener, about the critical nuance here that often gets glossed over. While the target itself received 2.05 MJ of laser energy and produced 3.15 MJ of fusion energy, the lasers themselves, they didn't just appear out of thin air, right? They needed power.
That's the absolutely critical context. Those 192 incredibly powerful NIF lasers required a massive amount of electrical energy from the grid to power them up and fire that 2.05 MJ pulse of light.
Energy.
Approximately 300 megajoules MJ of energy drawn from the electrical grid was needed to energize the laser's amplifiers and systems to produce that single 2.05 MJ shot onto the target.
Okay, wait. 300 MJ in from the grid to get 3.15 MJ out from the fusion reaction.
That's correct. So while they achieved Q1 at the target, fusion energy out versus laser energy on target, the overall wall plug efficiency of the entire NIF system for that shot was actually very low, about 1%. You put 300 MJ of electrical energy in, and you got 3.15 MJ of fusion energy out.
So what does this all mean for the dream of practical fusion power? Is this still a massive leap forward, or does this context change things?
It's undeniably a massive leap forward scientifically. It's crucial not to understate that. Proving ignition is possible is fundamental, but this distinction is absolutely vital for understanding the path towards actual power generation. This fundamental difference between energy break-even at the target, the Q target factor 1, and the overall energy balance at the plant level, sometimes called Kengineering or Q plant, which was 1, demonstrates a crucial point. While the scientific problem of achieving ignition, proving that a fusion reaction can indeed sustain itself and produce net energy at the target physics level, has now been solved, the engineering challenge of creating an efficient, practical, and repetitive system with the net energy gain for the electrical grid remains a very significant one.
So science achieved, engineering challenge remains.
Exactly. It's an absolutely huge step forward in physics, confirming a capability we only theorized and simulated before. But it's crucial to understand this context when we talk about fusion as a future power source. The path from demonstrating scientific ignition in a single shot on a complex experimental facility like NEF to building an actual power plant that continuously puts more energy into the grid than it consumes overall is still a very significant journey. It requires vastly more efficient lasers, targets that can be mass-produced cheaply, and a reaction chamber and energy conversion system designed for high repetition rates, many shots per second, and long-term durability.
Okay, so we've talked about the two main ways to tame the plasma magnetic fields in Tokamaks and Stellarators, or laser shockwaves in ICF. And we've even achieved scientific ignition, that Q1 at the target level with NEF. That sounds like huge progress.
It absolutely is. Decades of work culminating in that.
But, as you just highlighted with the NIF example, getting the plasma physics right is just the first hurdle, albeit a massive one. It seems that really significant challenges that extend far beyond pure plasma physics are now coming into sharper focus, especially the unrelenting impact of those high-energy neutrons carrying 14.1 MeV of energy in DT fusion on the reactor's actual physical structures. This isn't just a minor maintenance issue, is it? It sounds like a fundamental, maybe even existential obstacle for long-term operation.
It really is. You could argue it's the biggest remaining challenge for making DT fusion a commercial reality. It's truly a material scientist's nightmare.
A nightmare. Why so dramatic?
Because the conditions are just so extreme and unprecedented, the continuous bombardment from these highly energetic neutrons is like nothing else we engineer materials for on Earth. These neutrons, because they have no charge, aren't deflected by magnetic fields. They fly right out of the plasma and slam into the reactor walls, a breeding blanket, the vacuum vessel, everything.
And what do they do when they hit?
They literally knock atoms out of their fixed positions in the crystal lattices within the structural materials. Imagine a rack of billiard balls, and you fire another ball into it at high speed. Atoms get displaced, creating vacancies, empty spots, and interstitials. Atoms knocked into places they shouldn't be.
Okay, so it messes up the structure at an atomic level.
Profoundly, and this happens constantly, billions of times per second per square centimeter. Over time, these defects accumulate, and they lead to significant material degradation.
Degradation like what? Rusting?
Much worse than rusting. We see several major effects. First, a loss of mechanical properties like ductility, the ability to deform without fracturing, and fracture toughness. The materials become brittle, a process called embrittlement. A brittle material under stress doesn't bend, it just shatters. Not good for a structure under pressure.
Definitely not.
Second, we see radiation-induced swelling. The accumulation of defects, particularly helium gas bubbles produced by certain nuclear reactions, can cause the material to literally expand and deform, changing its shape and potentially causing components to jam or fail. Third, enhanced cracking and creep, where the material slowly deforms under stress even below its normal yield point. And fourth, the neutrons themselves can transmute atoms within the material into different elements through nuclear reactions. This changes the material's composition and can produce long-lived radioactive isotopes, adding to the waste management challenge.
Wow. Embrittlement, swelling, cracking, transmutation. It sounds like the reactor is actively trying to destroy itself from the inside out.
In a way, yes. And this damage isn't just limited to the primary containment structure. It can even affect critical components like the superconducting magnets used in tokamaks and stellarators. stellarators. Neutrons penetrating the shielding can heat the magnets or damage the superconducting material itself, suppressing their ability to carry huge currents without resistance, which is essential for creating those strong magnetic fields.
It sounds like a fundamental limit. Is there any material known on Earth that can truly withstand such conditions for, say, the 30–40-year lifespan of a power plant? Or are we talking about needing to invent entirely new classes of materials from scratch?
That's the multi-billion-dollar question. It's a profound challenge. It implies that even if we can perfectly bottle the star in terms of plasma physics, we then need to engineer the bottle itself, using materials potentially more resilient than anything found naturally on Earth, pushing the very boundaries of material science into uncharted territory.
So what are people working on? What are the proposed solutions to this incredible materials challenge?
The development of new, highly radiation-resistant materials is a top priority globally. There's a huge amount of research focused here. Several classes of materials are being investigated. For the first wall, the material layer directly facing the plasma tungsten is a strong candidate. Why? It has an incredibly high melting temperature, over 3,400 degrees C, and it's very resistant to erosion or sputtering caused by plasma particles hitting it.
Sounds good. What's the catch?
The catches are significant. Tungsten is inherently brittle at temperatures below about 400 degrees C, making fabrication and handling difficult. And under that intense neutron bombardment, it still suffers radiation damage, becoming even more brittle. Plus, as I mentioned, it transmutes into other elements like rhenium and osmium, which are also radioactive and can affect its properties.
Okay, so tungsten for the front line, maybe. What about the main structure behind it, like the breeding blanket?
For the structural components, particularly in the tritium breeding blanket zone where temperatures might be slightly lower but the neutron flux is still intense, the primary candidates right now are so-called reduced activation ferritic martensitic steels, or RAFM steels.
Reduced activation, meaning?
Meaning they're specially designed alloys where elements that would typically become highly radioactive with long half-lives under neutron bombardment, like nickel or molybdenum in traditional steels, are replaced with elements like chromium, tungsten, vanadium, tantalum that produce isotopes with shorter half-lives. The idea is that the material becomes significantly less radioactive much more quickly after removal from the reactor, simplifying maintenance and eventual waste disposal. Eurofer in Europe and F82H in Japan are examples.
But they still face damage issues.
Oh yes, they still suffer from embrittlement and other radiation effects, though they are being optimized to resist it better than standard steels. Their operating temperature window is also somewhat limited. Then there are other, perhaps more advanced candidates being explored, like vanadium, chromium, titanium alloys, VCR-Ti. These show promise with good high-temperature strength and potentially even lower activation properties than RAFM steels.
That's always a but.
The but here is twofold. Vanadium alloys are susceptible to contamination from impurities like oxygen, nitrogen, and hydrogen, which can degrade their properties. And perhaps more significantly, a large-scale industrial supply chain and manufacturing capability for these specialized alloys simply doesn't exist yet. We know how to make steel by the megaton. Making high-purity vanadium alloys at scale is a whole different challenge.
So it really comes down to this. Can we actually engineer materials and then manufacture them at scale to withstand conditions found literally nowhere else on Earth or even in our solar system outside the core of a star?
That's the core question. It's pushing materials science and manufacturing technology to unprecedented levels. It might require entirely new computational material design approaches, advanced manufacturing techniques, and extensive testing facilities that can replicate these harsh neutron environments, which are themselves very difficult and expensive to build. It's arguably the longest pole in the tent for DT fusion.
Okay, let's circle back to tritium. We talked about its scarcity and the absolute need for future reactors to breed their own fuel, using those neutrons interacting with lithium in the blanket. It sounds simple in concept. Neutron hits lithium, makes tritium, but making it work reliably and efficiently seems like another major engineering hurdle. What exactly does closing that fuel cycle entail in practice?
You're right, the concept is straightforward, but the implementation is incredibly complex. As we established, due to the natural scarcity and short half-life of tritium, any commercial DDT fusion reactor must be self-sufficient. It needs to produce at least as much tritium as it consumes in the fusion reaction, ideally slightly more to account for losses and decay, and to build up an initial inventory for starting new reactors. This target is called achieving a tritium breeding ratio, or TBR, greater than 1.
TBR1.
This is achieved, as we said, in the breeding blanket surrounding the plasma. Lithium, in some chemical form, is the key ingredient. The 14 MeV neutrons from the DT reaction fly into the blanket. Some neutrons will react with lithium-6 to produce tritium and helium. Other neutrons might react with lithium-7, also producing tritium but consuming a neutron in the process. Some neutrons will inevitably be captured by structural materials or leak out. To ensure TBR1, designers often include neutron multipliers in the blanket materials like beryllium or lead. When a high-energy neutron hits these materials, they can knock out 2 or more lower-energy neutrons, effectively multiplying the neutron population available for breeding with lithium.
Wow, okay, so designing the blanket is a complex nuclear engineering balancing act.
Absolutely. You need to maximize tritium production while also efficiently capturing the neutron's kinetic energy as heat for electricity generation, all while using materials that can withstand the heat and radiation and ensuring the whole structure is sound.
But the challenge doesn't end with just making the tritium in the blanket, right? You have to get it out.
Exactly. That's a huge part of the challenge. The tritium produced within the solid ceramic breeder pebbles or dissolved in the molten salt needs to be efficiently extracted or recovered from the blanket material, usually by flowing a purge gas like helium through it or using chemical processing for liquid breeders.
And tritium is radioactive.
Yes, and it's hydrogen, the lightest element. It's notoriously difficult to contain because it's a small molecule, T2 or HT gas, and can permeate through materials, especially at high temperatures. So you need sophisticated tritium extraction and processing systems that can handle large throughputs with extremely low leak rates to ensure safety and minimize environmental release. Then, the extracted tritium needs to be purified, potentially separated from other hydrogen isotope, stored safely, and accurately metered before being re-injected back into the plasma chamber as fuel. The entire system has to work continuously and reliably.
What kind of efficiency do you need for recovery?
The recovery efficiency from the blanket and the processing systems needs to be incredibly high, probably upwards of 95%, maybe even closer to 99%, to maintain the reactor's fuel inventory and achieve that overall TBR1 target. Any significant losses in the cycle make self-sufficiency impossible.
So if we connect this to the bigger picture,
The entire tritium fuel cycle, from optimizing the breeding blanket design for TBR1 to developing robust and highly efficient extraction and purification technologies, to managing the tritium inventory safely and accurately, and implementing stringent safety protocols to handle a large quantity of radioactive gas represents a massive integrated engineering challenge. It's just as critical as the plasma physics or the material science for making practical fusion power a reality. ITER will be testing several different blanket modules and tritium processing concepts to gain crucial data in this area.
okay, so let's assume we've solved the plasma confinement, we've got materials that can somehow withstand the neutrons, and we've successfully bred and recovered enough tritium to keep the fire burning. We have a self-sustaining fusion reaction humming away. How do we actually turn that incredible nuclear power into usable electricity that comes out of our wall sockets? It's not just about making a fancy glow inside a complex machine, after all.
Right. It's easy to get lost in the exotic physics of the plasma core, but at the end of the day, a fusion reactor is meant to be a power plant. And while most of the really groundbreaking research focuses, understandably, on achieving and sustaining the fusion reaction itself, an equally crucial, though perhaps less glamorous challenge is the practical conversion of the reaction's energy into usable electricity.
How does that work in a DT reactor? Where does the energy actually go?
In DT fusion, remember, about 80% of the energy released comes out in the form of kinetic energy of those fast neutrons. The other 20% is carried by the alpha particles, helium nuclei, which mostly stay within the plasma and help keep it hot.
So the neutrons carry most of the usable power.
Exactly. These high-energy neutrons fly out, pass through the first wall, and deposit their kinetic energy primarily within the breeding blanket and surrounding structures, basically by colliding with the atoms there and heating them up.
So the blanket gets hot. Very hot.
Very hot indeed. Hundreds of degrees Celsius, potentially up to 600, 700 degrees C, or even higher, depending on the design and materials. This heat, captured in the blanket material or coolant flowing through it, like helium gas, water, or molten salt, is then the primary energy source we need to harness.
And how do we turn that heat into electricity? Is it some futuristic, fusion-specific method?
Actually, no. The proposed method is surprisingly conventional. That heat captured from the blanket is transferred, usually via heat exchangers, to a secondary coolant loop, typically used to boil water into high-pressure steam.
Just like in existing power plants.
Exactly. That steam then drives large turbines, the turbines spin generators, and the generators produce electricity. This whole process, heat to steam to turbine to generator, is directly analogous to how electricity is generated in a conventional nuclear fission power plant, or even in a coal or natural gas-fired power plant. The fusion core is just a novel, high-tech heat source replacing the fission reactor core or the fossil fuel boiler.
So it's not just about building the star in a bottle, that incredibly complex fusion core, but also about building the entire, more conventional but still challenging power plant infrastructure around it.
Ensuring all that traditional energy conversion equipment is efficient and robust enough to work reliably in this completely new operating environment. Precisely. The efficiency and reliability of this balance of plant equipment, which encompasses everything from the primary coolant loops, the heat exchangers, the steam generators, the turbines, the electrical generators, the massive cooling systems like cooling towers to condense the steam, plus all the auxiliary systems like the vacuum pumps, the cryogenic plants for superconducting magnets, the magnet power supplies, remote handling systems for maintenance in radioactive areas, control systems, safety systems. It's a huge list.
Right.
The performance and cost of all this balance of plant equipment will directly impact the overall net electrical output and, crucially, the economic viability of a future fusion power plant. These auxiliary systems are incredibly complex in their own right, must operate reliably for decades, potentially in proximity to radiation fields, and represent a significant fraction of the total plant costs.
So it really drives home the point.
It really emphasizes that delivering fusion power is a holistic engineering challenge. It's not just a plasma physics puzzle or just a material science problem or just a tritium breeding issue. You need to get all the pieces right, integrated together, including the relatively conventional but still complex power conversion side, to make fusion a viable, reliable, and economically competitive energy source for the grid.
So the world of fusion development, it feels like it's undergone a really fundamental shift in just the last, say, 5 to 10 years. Historically, as we've discussed, it was almost exclusively the domain of huge, multi-decade, publicly funded international projects. Think ITER. That was the
I mean, it
model.
was definitely the dominant model for a long time, yeah. Necessary for tackling the huge scientific questions at scale.
But now that model seems to be fundamentally evolving, or at least being supplemented. We're seeing new players, new approaches, and new dynamics entering the field.
Absolutely. There's been a very noticeable shift. The U.S. Department of Energy, DOE, for example, has explicitly introduced what they call a bold decadal strategy for fusion. A key part of this strategy is shifting the focus significantly towards fostering public-private partnerships, specifically to accelerate the commercialization of fusion energy.
So not just the science, but getting it to market.
Exactly. In this new dynamic, you still have those essential large-scale public projects like ITER, continuing their vital work, validating the fundamental science, tackling the huge integrated engineering challenges on an almost unprecedented scale, and generating crucial data for everyone. They lay the scientific groundwork. But alongside them, you now have a rapidly growing ecosystem of private fusion companies. Companies like Commonwealth Fusion Systems, Helion Energy, TA Technologies, Zap Energy, Tokamaks Energy. The list keeps growing. These companies are often taking a more agile, arguably more risk-tolerant approach.
How so? What are they doing differently?
Many are attempting to find potentially faster and maybe cheaper paths to a commercially viable fusion pilot plant, often using smaller, more innovative, and sometimes quite different fusion concepts compared to the mainline Tokamaks and Stellarator approaches. They're often backed by significant venture capital or private equity funding.
Are they just building smaller tokamaks, or are they exploring really different ideas?
It's a real mix, which is part of what makes it exciting. Some are indeed pursuing advanced, high-field tokamaks, leveraging new superconducting magnet technology, aiming for smaller, potentially faster-to-build devices than ITER. Commonwealth Fusion Systems is the key example there, spinning out of MIT. Others are exploring completely different confinement concepts. We're seeing renewed interest in concepts like Z-pinches, like Zap Energy, where powerful electrical currents flowing through the plasma create their own magnetic field that pinches and heats the plasma. There are companies working on field reverse configurations, or FRCs, like Helion Energy and TE Technologies, which aim to create compact, self-contained rings or plasmoids of plasma that might offer advantages in reactor simplicity. And there are even approaches like magneto-inertial fusion, MI, which try to blend elements of both magnetic and inertial confinement, using magnetic fields to pre-compress or insulate the fuel before a faster final compression. General fusion with their magnetized target fusion is an example.
Wow, so it's a real Cambrian explosion of different ideas.
It kind of feels like that, yeah. Each approach offers different potential advantages, maybe in terms of smaller size, lower potential cost, different engineering challenges, maybe avoiding the tritium breeding issue by aiming for different fuel cycles initially. Of course, they often trade off something else, perhaps lower confinement times or stability challenges that still need to be overcome.
This raises an important question then.
Hmm.
Does this new hybrid approach this blend of large public science projects and agile private ventures exploring diverse paths? Does it genuinely accelerate the overall timeline for getting fusion power online? Or does it potentially add layers of complexity, fragmentation, maybe even duplication of effort?
That's the big debate, isn't it? It's a fascinating, unfolding experiment in how best to drive progress in such a complex, long-term technology. The proponents argue that the private sector brings speed, focus, innovation driven by commercial incentives, and access to vast pools of private capital. They believe it will absolutely accelerate things. The counterargument, or maybe just a note of caution, is that fusion is still incredibly hard, facing fundamental science and engineering challenges, like materials and tritium, that might require the scale and resources only governments can provide consistently over decades. There's also the risk of hype outpacing reality, or resources getting spread too thin across too many long-shot approaches. But most people in the field seem to agree that this combination, public foundational science plus private innovation and commercial drive, is probably our best bet for making rapid progress now. It seems crucial for tackling both the deep science and the practical engineering needed to get fusion power onto the grid sooner rather than later.
And this new landscape, especially the emergence of all these private companies, has clearly triggered an unprecedented influx of capital into the private fusion sector. The funding numbers we're seeing are pretty staggering. It's not just government budgets anymore.
No, the funding frenzy, as you called it, is undeniably real and has been accelerating dramatically. According to the latest report from the Fusion Industry Association, the FIA, which tracks the private fusion industry, their member companies raised a record high $2.64 billion in private investment in just the 12 months leading up to July 2025.
$2.6 billion in 1 year.
In 1 year alone, yes. And that amount was nearly 3 times greater than the amount raised in the previous year. So the acceleration is clear.
Wow. What about the total amount invested privately so far?
The FIA report states that the total cumulative private investment since roughly 2021 has increased fivefold, reaching an impressive $9.766 billion by mid-2025. So nearly $10 billion in private money has flowed into these companies in just a few years.
That's serious money. Does it come with serious optimism?
It certainly seems to. This wave of funding is clearly accompanied by, or perhaps driving, a high degree of confidence across the industry. In the same FIA survey, 84% of the responding companies said they believed that a commercially viable fusion reactor would actually be online and delivering power by the end of the 2030s.
By the end of the 2030s. That's incredibly soon, considering the challenges we've just discussed.
It is ambitious, yes, but that's the level of optimism currently permeating the private sector. This represents a very significant vote of confidence from the financial community. Venture capitalists, sovereign wealth funds, private equity, even major corporations are placing bets that fusion is not just a long-term scientific dream anymore, but potentially a tangible, maybe even profitable future industry within the next 10-15 years.
Okay, nearly $10 billion invested privately. Strong belief in deployment within the 2030s. It almost sounds, dare I say it, too good to be true. Is there a catch? Or maybe a paradox lurking within these impressive figures?
There absolutely is a paradox, or at least a stark reality check needed alongside the optimism. Despite that nearly $10 billion raised and the bullish timelines, the very same FIA survey revealed that 83% of the companies still identify access to sufficient investment as a major challenge going forward.
Wait, even after raising billions, funding is still a major challenge. How much more do they think they need?
Get ready for this number. The companies estimated collectively that it would actually take approximately $77 billion to design, build, and commission their first-of-a-kind pilot plants.
$77 billion. That's nearly 8 times the amount of private capital raised to date.
Exactly. And that $77 billion isn't necessarily for full commercial rollout. It's just to get those crucial first pilot plants, the ones intended to demonstrate net electricity production to the grid, reliably actually built and operating.
Okay, that puts the $10 billion raised so far into perspective. It's just a fraction of what's needed.
It really highlights the massive capital intensity of this endeavor. That $77 billion reflects the cost not just of the core fusion device, but of scaling up manufacturing infrastructure, developing robust supply chains for highly specialized components like high-temp superconductors or radiation-hardened electronics, building the full balance of plant, integrating comprehensive safety and remote handling systems, and going through the regulatory and licensing process. It's the transition from successful physics experiments to building actual industrial power generation facilities. That's a different beast entirely.
So what's the takeaway here?
The takeaway is that while the initial billions pouring in are a fantastic signal of growing investor confidence and are certainly enabling rapid progress in R&D and prototype development, they're really just a down payment on the incredibly long and expensive road to actual commercial viability. The greatest remaining challenge for fusion, therefore, might not be any single technical problem anymore, although materials and tritium are still huge hurdles. It might actually be securing the sustained, massive, long-term funding required, coupled with the sheer industrial-scale project management and execution needed to actually get fusion power from these exciting prototypes onto the grid at scale. It's a question of enduring financial commitment, finding patient capital willing to wait potentially decades for returns, and mastering industrial-scale execution, not just scientific discovery.
Okay, so assuming the technology hurdles are eventually overcome, and assuming that massive $77 billion, and likely more beyond that, can be raised, there's still the question of economics. Even with practically inexhaustible fuel like deuterium from seawater, the idea that fusion energy will automatically be too cheap to meter seems unlikely, given the incredible complexity and presumably high capital cost of building these reactors in the first place.
That's absolutely right. The free fuel argument only goes so far. The cost of the fuel itself, deuterium and lithium, is expected to be a negligible fraction of the overall cost of electricity from fusion. The dominant cost driver will be the upfront capital cost of building the power plant. The complex fusion core, the magnets, the lasers, the tritium systems, the balance of plant, all of it.
So what does it actually take for fusion to be genuinely competitive with other energy sources already on the grid, like solar, wind, natural gas, or even advanced fission? Is there a target price?
Yes, there is. To be truly competitive in future electricity markets, the generally accepted target for the levelized cost of electricity, or LCOE, for a fusion power plant is somewhere in the range of approximately $80 to $100 per megawatt hour, MWH, when measured in today's money, say $2020.
What exactly is LCOE again?
Levelized cost of electricity is a standard metric used to compare the lifetime costs of different electricity generation technologies. It essentially averages the total cost of building the plant, capital cost, paying for fuel, operating and maintaining it, and eventually decommissioning it, all divided by the total amount of electricity the plant is expected to produce over its entire operational lifetime. It gives you a cost per unit of energy, ML dollars, that allows for apples-to-apples comparisons.
Okay, so $80, $100 per mil-W is the target range to be competitive. How do we get there, given the likely high cost of the first few fusion plants?
That's the crux of the deployment challenge. Meeting this crucial economic goal will require a significant transition, a fundamental shift, away from the current model of building single, bespoke, one-off, highly experimental prototypes like ITER, or even the first private pilot plants. Those first-of-a-kind plants will inevitably be very expensive.
So we can't just keep building unique, groundbreaking reactors one at a time if we want affordable fusion power.
No, absolutely not. The path to competitive LCOE lies in standardization, learning curves, and mass production. We need to move towards building a fleet of reactors based on standardized designs.
A fleet? Like building cars on an assembly line instead of handcrafting each one.
Exactly that kind of transition. Building a fleet of reactors, perhaps dozens or hundreds, based on a common, optimized design, would achieve several critical things. It would allow for vital economies of scale in manufacturing components. It would leverage learning by doing, driving down costs with each subsequent unit built as manufacturers get more efficient. It would streamline supply chains. And, just as importantly, it would likely reduce construction timelines significantly compared to building unique prototypes every time. Both reducing the upfront capital cost and reducing the construction time, because time is money, especially for large capital projects, are essential for achieving commercial viability and making fusion a practical, affordable energy source that can actually be deployed widely enough to make a difference for climate change and energy security.
So the critical question then becomes,
Can an industry that has, for its entire history, relied on these monumental, decade-long, multi-billion-dollar, one-off national-scale R&D projects successfully pivot to an industrial manufacturing style approach? Can we move from pure research and bespoke engineering to standardized designs, factory production of components, and efficient assembly line construction on site? This represents a profound shift in mindset, in engineering culture, and in execution capability. It will require unprecedented collaboration between governments for things like regulatory frameworks and potentially loan guarantees, established industries who know how to build big things efficiently, and the innovative private fusion companies themselves to standardize designs where possible, streamline regulations, build robust global supply chains for specialized components, and develop the skilled workforce needed. It's the final, crucial bridge to cross from scientific possibility to economic reality. Hashtag outro.
So we've taken a really deep dive today into this incredible dream of a star in a bottle. A dream that feels like it has genuinely evolved from, a purely theoretical abstraction decades ago into a tangible, multidimensional, very real engineering problem that humanity is actively, aggressively working to solve right now.
It really has made that transition. And the recent scientific achievements, things like the historic ignition demonstrated at the National Ignition Facility and the record-breaking long-pulse high-performance operation of the Wendelstein 7X Stellarator, they've undeniably validated the fundamental physics. They've shown us that replicating these stellar processes, controlling fusion here on Earth, is indeed feasible.
It's just an amazing testament to human ingenuity, really.
It truly is, and the field of fusion is undeniably entering a completely new era now. It's being fueled by that unprecedented private investment we talked about, and it's characterized by this dynamic and frankly somewhat surprising collaboration emerging between the traditional public research efforts and the agile private sector. Now, immense challenges absolutely still remain, particularly in those crucial areas like developing truly long-lasting, radiation-resistant materials, establishing a completely closed and self-sufficient tritium breeding cycle that works reliably for years, and, maybe most dauntingly, achieving the industrial and economic scaling needed to make it competitive. Those are not small hurdles.
No.
But despite those hurdles, the remarkable pace of progress in just the last few years strongly indicates that fusion power is no longer just a distant dream, a concept perpetually 30 years away. It feels like a technology that is being actively built, tested, and advanced today with a real shot at contributing to our energy future.
It feels like it's no longer a question of if humanity can harness fusion power, but really when and how it will ultimately be achieved and deployed globally. For you, our listener, hopefully this journey into the world of fusion power offers a clearer glimpse into a future that could truly revolutionize our energy systems, maybe reshape geopolitics, and certainly have a profound impact on our environment in ways we can probably only begin to imagine right now.
So after this deep dive, what stands out most to you? What aspect of this quest for fusion energy seems most challenging or perhaps most exciting? How might this potential future impact the world you live in, and what new possibilities might it unlock if we succeed? The star awaits.